Yes. Okay, welcome to week number 2. I'm still excited to see still so many of you. Visible. How did the exercises go? We had 2 classes, yes? Wonderful. I'm also excited about that. Concerning the exercises.
It was mentioned in the exercise that there are some in-class worksheets.
Yes.
Is it going to be uploaded or is it just gonna be?
It was only really in class. I can upload them because they exist. I will then. And it probably will only be this very first time the in-class problems because you'll have to discuss other things. You'll have plenty of things to discuss. It was the first week because you didn't have anything really, and let's see, if a problem set is really short, really easy, and you would get bored otherwise, I'll pick them. But it's really no regular thing, but still, what we have, I'll upload and you'll find it soon in Moodle. Talking about Moodle, so and the exercises. I wasn't super precise, I guess. I wrote, you may submit your homework in groups or in teams of 2. And I meant to say, the default plus you may, the default is alone, yeah? So you don't have to find a group. There was a message, hey, I have to have a partner. I don't have a partner, what do I do? You can work on your own and you can work in teams of 2, and this has to be somehow realized on Moodle, so that one way of doing it would be you write your names, your 2 names on the sheet and submit it, and then, but then we have to do the bookkeeping ourselves. The teaching assistants have to then kind of write it somewhere. Maybe you put 3 names, maybe you forget, and it's complicated. So that's why we have this activity here. It says activity, individuals or teams for problem set 1. So you click there, let's say, let's click for the next week. And then I have, someone, and I want to work on my own. So I pick a team that doesn't have any member yet. And then I say here, okay, I want this, and shows. And if I want to work with him and he's Martin, then I don't know where Martin is because we agreed to meet in 1, but Martin isn't there. And then I go here, Gruppenmitglieder anzeigen, and I see, Martin right there. So this is my team, and then I pick him. And that has the advantage that Moodle does all the bookkeeping. You submit one of the team, and then we get only 1 document, they grade 1, and then they upload the answer, and both of you have the answers. It's very simple. Except for the confusing part, if you work on your own, you still have to create a team. And since I don't want to force you to work with one partner all the time, we might switch, and we have to do this every week. Not just once, then every week. It's not a big deal. It's just as hard as writing your names on it, which is hard, in fact. I know from it. Yeah, that makes sense. So there's one warning. I did the same procedure for the younger students, and they find every way to cheat because they're interested in that. I know you're not, but if there's, it's Wednesday evening at night and you haven't done anything, and you see, there's Svenja. Awesome. She's always amazing. I'll join that team. And then you have done all your homework and submission within those 15 minutes, right? But then Svenja will call up on you, or she, you have a new friend. I don't know. There's a loophole. And we had this, somebody has a partner who's never talked, who never worked together, but here, this is a partner. So you can watch out for this. I don't think it will be anything because you want to learn QFT in the end. That's that. Now, in the exercise class last week, we talked about relativistic quantum mechanics. We tried to make a theory which does both quantum mechanics, the discrete values for observables, the discrete energy spectrum, for example, plus the features of special relativity, which means speed limit, and also the E equals MC squared particle production. And the the naive thing was to take the relativistic dispersion relation, use the replacement of the coordinates and momenta by operators, and write down some Schrödinger-like equation. And we studied this, and we found funny things. For example, that the conserved density rho could be negative. It had different expression from what we had in non-relativistic quantum mechanics. In non-relativistic quantum mechanics, it was certainly positive, it could be zero, but otherwise positive, and had probability interpretation. And in the relativistic case, it doesn't. It can be negative as well. And we then agreed, oh, this is really a charge density. We have positive and negatively charged particles, particles and particles. It wasn't really any way of seeing that there's electric charge, but it's some sort of charge business going on. Particle and antiparticle. Antiparticles are counted as negative particles in a way. We'll make this precise how this is electric charge later, but now there was no charge business, no photons, no electricity, anything. It was just particles and antiparticles. And there was something, so if you have this negative, your group velocity, which is the current divided by the charge, never know whether I should put the dot there. This dot belongs to the J, it's not a time derivative. So if the current over the charge, if this is negative, then you have a different sign between J and V. So your current can flow one way, but it really means it's a particle going this way. So a particle going this way is an, what is it? Yeah, well, a particle this way is an antiparticle that way. And I wanted our teaching assistants to show you a little animation. Did you do your homework, by the way? Like this optional homework where I said, draw the partial waves, I said it in class, and see how they go, the partial waves, solutions to the Klein-Gordon equation are superpositions of partial waves. And all the partial waves go faster than the speed of light. Their phase velocity is faster than c, it's larger than c. Well, that's weird. You wanted relativistic theory. So the group velocity turns out to be smaller. And there's a nice picture. And I wanted you to see that picture. And I'm not sure, have you seen it? It didn't work in the first exercise, but then it did in the second. So here it is. I superimpose just 3 waves with wave numbers 9, 10, and 11, and these amplitudes. So it's just 3. And if you add 3 sine waves, basically, really it's exponentials that you add, and then for drawing this, I took the real part, you get this wonderful fish thing. So adding 3 sine curves interferes in a way that gets to 0 here and then maximum there. And now I let time go. I don't have a button. Where's my button? What are you seeing?
Seeing the wave packet move.
Do you see the wave packet move? You see what else moves? You see also
Of course, the individual.
the blue stuff moves. And now I have a red line. I didn't tell you what it was. This is a line that moves at the speed of light. This line moves at the speed of light. And now we're supposed to compare who's basically the fastest. The blues. Look at this blue maximum here. Where is it going? This runs away from the red line, and the next one catches up, and then it passes it in. So the blue is certainly faster than the red one. And so the partial waves go faster than the speed of light. And then you have this envelope here, and see where this maximum goes. This is left, hopefully, behind. Yeah, so it's much slower than this line. So this is how it looks like what you've seen last week in equations. Phase velocity larger than the speed of light, group velocity smaller. Nice. But we can do even better if there's this potential step and we come with a wave that has an energy much smaller than the step. Non-realistically, you have to be reflected. relativistically, if the step is high enough, there's an oscillating solution that goes through. But that was weird, right? That was this antiparticle business. So do you know how this worked? What do we expect to see there? It goes through, but in a weird way.
The energy is higher, or kinetic energy is lower than the potential.
The kinetic energy is lower than, yes. Everything's low. The total is oh yeah. Of this thing.
Has
No,
negative charge.
It then has this negative rho, but here talking about this, we have a phase velocity that moves in one direction, like backwards, but the particle is really going through. So it's this negative sign in the denominator. And the picture for this is here. So I gave it a little offset in energy. And come back to 0. And now I'm moving time. So the phase velocity is to the left. Obviously, the blue moves to the left. Resetting. The blue moves to the left. But still, the envelope, the orange, goes to the right. That's what's happening under the barrier. Well, that works. It's kind of, I thought it was cute. I wanted you to see this. So, quantum mechanics with quantum field theory. Second, quantization. It's really a cut. New week, it's a little cut. We ended up with the realization, if you do it the naive way, if you just use the Klein-Gordon equation, we end up with particle production, with antiparticles. So the particle number isn't fixed. You start with one particle, you get 3. You have this. So we have to kind of deal with it. The formalism doesn't work for multi-particles because if you have even if you say this is now not a particle density, it's a charge density, we don't know how many particles we have. We can't deduce from the charge density the particle number density. Say just we had classical particles. I told you we have one elementary charge. There could be one elementary charge. There could also be 2 plus and 1 negative. And so we don't know. It's not a good formalism. And this week, we will develop the formalism for multi-particle quantum mechanics, forgetting for now relativity. I'll start again. It doesn't matter. We just want the formalism that allows for the creation of particles. We don't want to say we have a fixed number. We want to have a formalism that allows for something to be created. And we can allow this also in a non-realistic setting. So that's why we forget about this and then we come back later. My main focus is really high energy in particle physics. So we talk about fundamental theories, like what do really these particles that make up nature, what interaction do they have, and then you do have relativity there. But you could also do this from a more solid state physics point of view, where you don't have fundamental particles, but quasi-particles. So the particle physicist would say, oh, you have the photon, this is a fundamental one, it's an oscillation of the electric field, something. But you could also say, hey, I have an acoustic wave. And that's an oscillation, something that propagates in a material, in a lattice or so. That's could also be a particle, like the photon. It's called the phonon. And it doesn't have to be relativistic at all, right? You can have other dispersion relations. I don't know where the person is. There was someone who was interested in solid state physics and graphene. Excitations in graphene behave as if they were relativistic, just not at the speed of light, but the lower one. Not there, somewhere at home.
I am an attendant.
Yes. Right, so I was working towards this. So what am I saying? I'm saying we'll do this many particle quantum mechanics now without relativity, and then we can go both directions in the elementary particle physics or also in the solid state physics direction. Probably beginning of next week. And the formalism that we will obtain is a quantum field theory. That's why we're talking about this in the first place. I first have to recall some things about quantum mechanics, and this is called one particle quantum mechanics. I want you all to have a proper start. And also, it'll be useful to know everything very well about quantum mechanics, because it's just going to get harder. And many of the conceptual problems that we'll have in field theory are exactly already there in quantum mechanics. So that's why I'm reviewing this. And you interrupt me when I have to go slower. How does this work? In the normal quantization, you have a classical theory, Hamilton operator, or let's say so it's one particle. We have one particle in one dimension. One dimension potential. And I call this potential phi of x. So with this one function, then we create a Hamilton operator, classical even. It's a function of p and x, and you have, if I do non-relativistic, you have the p squared over 2m plus v of x. And last week we just worked in the coordinate representation. When we quantize this theory, you just put the hats on there. So the Hamilton operator is this function with p replaced by p hat and x hat, and then we have p hat squared 2m plus v of x hat. And we have this just the x multiplication, and this is the derivative with respect to x, and now we keep it general, abstract. So these are just operators. And they said they are Hermitian. So if I take the adjoint, then it doesn't change. Basically saying the objects are real, and they don't commute. They can't exchange them. Can't change the order because if you changed, you get an IH bar. So this object is defined. It's called the commutator, and it's x p minus p x. Commutator. Maybe saying something new, no? Yes. And then we have the Schrödinger equation, which is h hat on some state e psi. We only know this h. We don't know the eigenstates. We don't know the eigenvalues. It's an equation that you solve for both. You usually find more than one solution. I label them by k. So, arrange for them to be orthonormal. If I have two solutions, the scalar to the inner product is 0. If I have if I take the square of a solution, then I get the normal I choose it to be 1 or less. And k runs over something. values. Now. What the are, depends, now here's the question, if I have an infinite well. Examples. Infinite well, how do the energies look like? Just roughly. The very back. Because I want people in the first row to come back to the first row, but you will come back, right?
Yeah, I
Yes.
mean, otherwise.
Infinite well.
So it's like first, so like the first zero
Not
energy.
a zero, so let's put zero somewhere. This is zero, and that's not a state. Yes.
And then you get like as you go up, the density of states gets higher. If I remember
The
correctly.
density gets higher. Do you mean that?
So.
The density?
I think like they're closer and closer. So like
What's an infinite well?
Yeah.
It means you have here either up or down. Let's say here's the potential in this range, zero, and then it's here it's infinite. That's why it's infinite well. So you have a part you can only sit in there.
Yeah.
That's what I mean. Well, I have to go to the last row.
that they like the distance between this distances goes up with square.
Exactly. Exactly. Not the density goes up, the distance between the states goes up. So the first one looks like the wave function looks like this. And if I want to squeeze in, I have to make sure that I go down to zero. Well, why is it here if I go to zero? I draw this at the height of the energy. Basically the same picture. Here's zero, and then there's this first energy. And now I want to squeeze in the next one. So I have to have this. How much higher is that? This has a wave number that is twice, wave number is the inverse wavelength. So the wavelength from here to here, this is half. So this is double of the wave number, but where's my P? P is H bar K, E is P squared, so that's E is K squared. If I double the wave number, I multiply the energy by 4, so this goes up by 4. Whatever this is, this thing is 4 times, so okay. And this is 1. The numbers don't matter, but usually you say E1, E2 rather than E0, E2 because you want the square. So E K is proportional to K squared. That's what we expect. Depends on this thing. So the next one is very up here. Next chance, what is the harmonic oscillator? Harmonic oscillator is the cute one.
Linear.
It's linear. Does it start at 0?
I think it depends on the potential. If there's a
The potential is just the square. The potential is 1/2 m omega squared x squared.
I think it goes to 0.
You can't, if you want it to be there,
Naturally,
then it's, it's too doesn't like it. You need to go a little further up. You don't have to go to 0. You have this bumping. So it's whatever it is, and then it goes linear. Funnily, there's a half a gap between 0 and the first. Anyway, it's K is proportional to K plus some constant is offset. You can set this to 0 by subtracting, so you're right. It depends on the potential. Yeah, push it that way. You want one more? One for you? It's not really called because I'm working in one dimension, but if you had this potential, like a 1/x, like this, say, is a potential.
I don't I don't know the energies. I would guess that like, no, this time.
Let's say the answer for the Coulomb, for the hydrogen atom.
Yeah, okay, there the, like again, we don't have a energy at 0. Yeah.
Oh, yeah, no,
Question.
sorry,
Like,
that's the potential.
Yeah.
We wanted bound.
I'm not, I think it was like, you also didn't have a 0 energy. I hope this is.
They're all negative. The bounce is all negative.
Okay, yeah. But
I'm taking the answer from before, the density gets bigger.
yeah,
Because it's easier to squeeze more in, you don't have to squeeze so hard because the potential widens. Right. My point is just, okay, you have this Schrödinger equation, you do operators, you get the states, and you get spectrum that's characteristic for your system, or whatever you have here. And I want to discuss now in detail the harmonic oscillator, because this is going to be relevant then for our multi-particle field. You should know all the formulas that have anything to do with the harmonic oscillator. So harmonic oscillator. The potential I wrote down is this thing. Let's write it again. E of x is 1/2 m omega squared x squared. The m is the same m that you have here. It's the mass of our single particle. And it appears that the potential, just so to make this energy spectrum nicer, and it depends only on this omega. Omega says how wide or how steep your things. So if omega is large, you have this potential, if small is this potential. And the Hamiltonian is now p squared over 2m plus this thing. Don't look at the constant, then you see something p operator square plus operator square. Square of these things separate. It turns out, you probably know, I've seen this many times, it turns out that it makes sense to factorize this thing. So you don't have a sum, but you have the product of two operators. And so you use the third binomial. If this was a minus sign, you would go like a plus b, a minus b. And then you have the difference factor. You don't have a difference, but I'll get to a difference by putting it high. I squared takes care of the difference. And now after some you come up with this idea, divide. It depends on where you want to plus and minuses. It's just cheap. So you want x hat plus, there's the I, m omega hat. And the other one is then the complex conjugate, is minus I over m omega hat. And then, just so that it looks nice, people add constants in front. M omega 2h bar. And this guy is now called operator alpha. And this is called, and this is called operator alpha dagger, because it indeed is the adjoint, the Hermitian conjugate of this. Real, so if I dagger this, there's none there. Here's an I, turns into minus, the P is real, and then it really is what it is. And if I multiply these things together, like here, then I get that object. But I also get stuff that I don't want, because H and P don't commute. So I do this in both orders. I do H as alpha dagger alpha once, and I also do it the other way around. And if I add the two, the mixed terms go away. And then I have almost this thing. you get the h bar omega a half, and this h from above is this. I know I haven't derived it, but I assume that you have seen this. It's also a boring computation. Really, the idea is to factorize it, and that's how it works, and you can fix the details if you like. You know, it's nice to work with this. Why? This is the canonical commutation relation that turns into alpha dagger equals 1. Like 1 in the sense of unit operator, but often here even these are operators acting on states. This is an operator acting on a state, but you don't see really an operator. There's nothing but a hat. I will try to put on every operator there is a hat until the end of the semester. Usually people in the books skip that really soon. But just let me be, yeah?
Why is the P real, the operator, momentum operator? We had it, the correspondence principle, it was
It is, so first of all observables are realized by Hermitian operators, because only the Hermitian operators have guaranteed real eigenvalues. So that's what we really want. If we have a non-Hermitian operator, we get stuff that we can't identify with the measurements and observables. So that's why we want it. Now the question is, why is that particular one that you know looks like this? In what sense is this Hermitian? Is that the question?
yeah, because I thought you said it was real. Okay.
Yeah, it is real, in the Hermitian sense, as in like, but you're talking about this eye, right? Because that one is annoying. So what is adjoint? What am I saying? So given, I don't know how to say this. So you have an A, the adjoint A dagger is the operator which makes this psi, you know, let's do it as a scalar product, psi A pi equals A dagger psi chi an identity. So if you're in a scalar product and you act on one state, you can also decide you want to act on the other one, but then you can't act with the same guy. You have to have something else that corresponds to it, and that is then called the adjoint. This equation here sometimes looks like this: psi A chi equals A dagger psi chi. Maybe less brackets, less confusing. This acts here, or you act on the state to the left, but it's not the same thing. If the operator, if this operator joined to this, it really turns out to be the same, you call it Hermitian. This thing here satisfies this equation with the same P here and there. So now we go to the coordinate representation. The short has there's one partial integration involved. This is no, it's not good. The scalar product here, so this one, psi A pi is integral psi star x, sorry, A, now I want P. P is minus I H bar dx. Psi. Let's just write the others. I mean, you can now, oh, now if you argue, I want to bring the I, okay, listen. I want to bring the I underneath him. Under the star, so I have minus I H bar psi all star. Now it's wrong. Like now it's wrong because the I moved under the star, so I have to add a minus sign to make. Are you following? Does it make any sense?
I understand. My question is answered already. It was just misunderstanding, but I understand. I know this. I don't remember.
Now unfortunately, I have to partially negate once. If I push this here, then the minus sign goes away, and then indeed, just so I don't stop midway, it's the same. Blah 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 blah. See, hi. Now, what was your question then?
It was. It's kind of unrelated. I
never mind.
answered already.
Good. I was talking about if there's nothing, it means an identity operator. So here, whatever you want, identity operator or just one or one times identity operator. What I mean, right? And this is exercise. Very short exercise, plug in these things to the commutator, and then you find this. Well, that's beautiful, but too complicated, so let's do it that way. And now we compute the commutator of H with alpha dagger. The H is this guy, 1/2 H bar omega alpha plus alpha with alpha dagger. Now, if you aren't familiar with these commutator and oscillator computations, you have to do many of them. I gave you some on the exercise. But so if I have, so this goes front, the sum you can split up. So it's this with this plus the commutator of this with this. So let's worry about the commutator of these two with this guy. And then it's like the product rule. It's these two together, with this two. So something I need to write, right? So it is with this one, and then this one stays behind because we're behind this one, plus, and now this one moves out of the bracket, and then you have alpha at alpha thing. So that's the commutator of the first term with this, and then the plus the same thing except for the hats move alpha hat dagger plus alpha hat alpha what have you. Now that's obviously 0 because it just means this times plus minus the opposite, so that's 0. This is 1, this is 1, this is 0, and then we have two type. These two alpha dagger twice, so it's H bar omega alpha dagger. So this one is important. And you can also do the same thing with the other one, the Hermitian conjugate, and you can do it in various ways. You either do the same computation, the commutator. You could also conjugate this equation. Let's conjugate this just for fun. So we have that is equal to H bar omega alpha dagger. So let's just conjugate this equation for fun. It conjugates in a product, it conjugates every factor, but also reverses the factors in the product. So this thing is alpha dagger, dagger, H, dagger. Then you have real constant, and this is alpha dagger. Dagger twice is nothing. Twice is nothing, so this is alpha. And that one is an Hermitian operator, observable, or you look at it here. And on the other side, we have this. And now I want them in the other order. So I turn them around, but this is anti-symmetric. So I have H alpha equals minus, so it's minus sign, bring it on the other side. And this. So that's partner. The one without the dagger is minus, the one with the dagger is plus. That's how I remember it. The dagger looks like a plus, so the number there, plus and there, well, looks like a minus sign, or it doesn't, it's not a plus, so what can you do? And that's important. These things are important. Some operator, so basically this alpha is an eigenstate or an eigenoperator to this H. And that identifies the alpha and alpha dagger as raising and lowering operators. So if I say psi is a state with energy E. Did you write E and go E? I take E to make it obvious. A state with an E in it is a state with energy E. That means, i.e., this means H on E is E. E, lots of these. Then alpha hat dagger on E. This object has a little bit more energy. It's also an eigenstate. It raises the energy by a certain amount. So this thing can be written as, so I have H alpha dagger E. This is really what it is. I don't need the parentheses. And now here I am going to insert a commutator. This means adding or subtracting the reverse. I wasn't allowed to, so I'm adding back in the reverse. This is now correct. There wasn't a commutator, now there's one, but this makes up for it. Second term. I did this because here I can use H bar omega alpha dagger. This equation. This is by definition of the state E times E. And now it looks like a dagger on E, a dagger on E, and one has this. I can add E plus H bar omega alpha dagger E. So the state alpha dagger E is an eigenstate. Again, it also has a certain energy, and it's the E from this state plus something. So that's why alpha, like raising operator. And if you do angular momentum, you also have raising operators. You can raise everything. You can also raise the Z component of your angular momentum vector by the L plus minus. It's the same story. If you see something like this, an operator commutator with something else is proportional to that something else. You know that the something else raises the eigenvalues of that operator by whatever the constant is. And here he raises it by minus H bar omega, so we call it lowering operator. Why am I doing this? Because, as I just said, you can many things, not just energies. What do we want to raise and lower? You probably forgot because it was long ago and we talked about it. What are we going to raise and lower? particle numbers. So we are going to use this now, what we learned here in the quantum mechanics context, just copy the formulas to a very different context. But we know that it works, and so we interpret them in a different way. This is how we're going to create the particles. There's more, I guess. You're not even doing so bad in time. And this is where it goes down. Whenever I realize I'm not too slow, I'll get so slow that we're not going to finish. Do you have questions? Was I too fast? What's their business? I don't. Yes.
Just very quick, what happened again if you lower the lowest state?
Which
I
lowest?
forgot what happened.
Which lowest?
Try to.
We haven't even figured out there's a lowest.
Okay.
Let's do this. How do you know there's a lowest? In fact, there is a lowest. You know, we have this potential. It has zero at the very least. How can it be lower? But how do you do it? You say the following. So let psi be absolutely any state, not an energy eigenstate, doesn't have to be normalized, just anything. Then we can compute the expectation value of H in that state. Now, where's my H? It was a half H bar omega psi alpha dagger alpha psi plus, let's do it even slower. No. Psi alpha alpha dagger psi. You know, where was it? It's gone, right? You remember the structure, the square here and the square once the dagger was the first and the second plus that was this thing. And I have this one. This is wonderful. Now we can learn something or reinforce something which you already knew. This operator is now acting to the right. Well, it can, it's sitting there, all want to act on the right. Now we want to act on the left. But we can't just act with this one on the left-hand side. We have to use its adjoint. So this is equal to alpha dagger dagger, which is nothing on psi. And then we have the alpha psi there. So I can write it like this. Also, what's happening here? Here it's in front of the cat, here it's inside. Everything that's inside these things is a label. Everything that's outside here is an operator. And the operator has an action on the states and creates something new. And you can give that whole thing the label, which is a composition of the name of the operator in the original. So that's what is happening here. After having acted with alpha on psi, I have a new state that I label by what have I done to the psi. Okay, now this is the square of this. If you want, you can write it as alpha psi, the norm squared, and that is by norm's fault positive. Or zero, it's zero if this is a zero vector. And here it's the same. You bring this on the other side, so this is equal to the norm of alpha dagger side, but still it's positive. It's positive somewhere. So the whole thing is larger or equal to zero. So the eigenvalues of H. So H, yeah, it has to be positive. So all it, if you diagonalize all the eigenvalues have to be positive. And if I have a state and to lower it, at some point, the eigenvalue there would be negative, which can't exist. So then you conclude there must be one lowest that gets killed. So there must be one state, which is wonderful for our purposes because we don't want less than zero particle. Zero particle is cool, but then no less. So there must exist, or they exist, there must exist a state with lowest energy, call it alpha, call it psi zero. And the property now is that it can be lowered, right? Alpha on this thing can't be a new state, so what are the options? Zero. And what is the energy of this guy? It's the lowest. Is it zero? I don't know. Is it, let's say, H on our state psi zero? It was 1/2 H bar omega alpha dagger alpha plus alpha alpha dagger on psi zero. Now we act. The first one is easy. If this acts here, it does zero exactly. This is the easy one. So let's just get rid of it. 1/2 H bar omega alpha alpha dagger. That's the hard one. What is alpha dagger on the lowest state?
Like with it's a rising operator.
Yeah.
So we get H bar, ich meine alpha plus H omega for acting on the lowest state.
No. No. If you would act with H on this, you're right. That is going to be the lowest energy, whichever that is, we're trying to figure this out, plus one more. Right? This is what you're doing. Is that what you're doing? So the energy, but that's not what it says. It says alpha dagger on this. We know this guy has 1 unit more, like 1 H bar omega more than the lowest energy. So what, right? I still don't know what this is. I know if I act with H on this, what I get, but I'm not acting with H on this. So nice, but can't use it.
I think it just raises the state one.
It raises the state. Well, I can give this a name. I don't know anything then. Say, I could write psi 1. I want to know what is E0, what's its energy. Oh, this is fun. Now this is a puzzle. How do we get? Yes,
wouldn't the most relaxed thing be to just use the commutator?
exactly. We will, this we don't need. Oh, this was so cute. We don't really, I mean, not quite yet. We don't know quite yet what the A dagger does, so we turn them around. So H on psi 0 is what we were repeating. And we ended up with this. Now, let's just add this guy in there. Now we made something wrong. We make it make up for this by adding the one with the other order. So alpha dagger alpha on psi 0. Why is this right? This commutator is what the first term of the commutator is what we had. The second term is minus this. We didn't have this, so we added in, and then that's cool. This is equal to 1, and this 0. So we didn't do anything wrong with it. And we end up with 1/2 H bar omega psi 0. And now we can read off, it has the energy, lowest energy is 1/2 H bar omega. And then, you know, it goes to units of H bar. Our spectrum is 1/2 H omega, 3/2 H bar omega, 5/2 H bar omega, 7/2 H bar omega, and so on. This is our Oh, I should have done this in the computer. So here. It's 1/2 h bar omega. So. Then we read on this. Then we see the whole spectrum EK is h bar omega 1/2 plus k, or k plus 1/2 with k 0, 1, 2, 3, and so on. And these are the states. Sometimes people I always like to draw boxes here. These boxes are really, and I can put the state in these boxes. So I have one particle, and I could put the particle somewhere in this box, right? These are the available states for it, the energy eigenstates. It can be a superposition, fine, but if I want an energy eigenstate, a state with a certain energy fixed without uncertainty, then I just pick a box. So now I have a particle there in a mean, the system is in the state of this energy, and I can move it around. And I move it around with these operators. So if I want to go up, then I apply the A dagger. If I want to go down, I apply the A. And then I can go further down, and I can go back up and up. But if I went down here, then there's no state, so I get a 0. Yeah, there's nothing really. And here it keeps going. So that's the graphical representation of your Hilbert space for the harmonic oscillator. You call it a Fock space, which means that you have sort of an object, an excitation that you can follow. You can give your state a number. And here it would be an excitation number. We will turn it into a particle number in a minute. But so far we have this. We have just this one state, one particle in this state, and we can move it around. Quantum mechanics would allow you this, right? You can actually do a fuzzy dot and a fuzzy dot there. Then my system is in a superposition. Psi1 plus psi2 with some coefficients. That works too, but doesn't mean that you have two particles. You just have a fuzzy, you can put it anywhere you want. Right? Then it isn't what you have. The energy eigenstates look like this, the wave function, and so on, but they don't move. It's the stationary state. If you want the oscillator to oscillate, you have to superimpose various solutions, and then you write this. My point is, it is still one particle. Yes?
And there when we have the rising operator by 0, then the by 1 will also then apply the lowering operator that's go back to
Exactly. We could have done that. However, we wouldn't know how much psi1 it is. In fact, it's a homework to figure out how much psi1 you get.
My idea would only that we don't care about psi 1 because they're lowering it. So you get.
No, you care. If you went up to psi1, then you can lower it. Go back to psi0. In fact, it makes sense, right? So this is psi0, you raise, you get psi1, you lower your psi0. But you could get a factor of, it could be that this thing is 2 psi1, and then alpha on psi1 is whatever, 3 psi0, the whole thing, and then we have a factor of 3. The energy would suddenly be 3 times as big. You don't know. So in fact, figure out homework alpha dagger on psi k is what? Of course it is psi k plus 1. But how much? How do you know how much it is? You want all of them to be normalized. So psi k could be 1. And well, you just put a number here. number n, depends on k. You compute the norm here of this state equals this state. You use on both sides, that means you figure out what it is. And the answer is, because we're gonna need it, is k plus one. It's not just one, it's gonna mess with it. If you go up and back down, you get a well, do you get a factor? What do we want? Where's our energy? Now I'm gonna say we don't get a factor. This is kind of weird. What's that?
Factor depends on K.
Yeah, I know, but he's so right. We don't. There is something, but it's gonna keep. Okay, let's see. If you do alpha, the down, you get square root k psi k minus 1. Which does make sense. If k is 0, you lower the 0, but you don't want anything, so you don't want a minus 1, and you don't because you have a 0 in front. So square root of 0 is 0, so then it kills it. It really kills. So these are the. This is what you're supposed to find. And let's do this now. So we have alpha dagger on size 0. Now let me do the k. Yes, because you got lucky. You got lucky. I don't want that. So I'll use the general k, okay? So we raise it once with this formula, then we have k plus 1. This one is still there, alpha, and then we have one level higher up. And now we lower it. And lowering by this means, what does that mean? We can use this formula, but with k plus 1 instead. So we really should think k plus 1 here, and then we should think k plus 1 there, and then we should think k there. And then this thing is square root k plus 1, and then psi k. And so we get 2 of them, and then we have psi k. All right, so this is k plus 1 psi k. So all I'm saying is if you first raise and then you lower, you don't necessarily end up with just 1 times this guy. And so you could make a mistake by going up and down. However, why are you lucky? If that is the 0 case, the bottom state, yes, you do with the bottom, and you get 0 plus 1, and that is 1, and so yeah. All right. So I was overcautious, which is not bad. No. Now we know everything. Now let's go to our many body theory. Time does permit. There you go. Hit. Many particle quantum mechanics. 3.2. We do this in 2 steps. First, we fix the number of particles to n. Fix the number n of particles. And actually we deal first with many, and then we make n average. We superimpose all of them. So we now have to have a Hilbert space, a space of states for many particles. Both, and also these particles should be non-interacting. We start by non-interacting particles, also fun. Yeah, well, the Hilbert space, we can also span when they interact, so let's don't worry about it. If the set psi k for k is some numbers, and I'm using the notation of what we just did, the harmonic oscillator, and you should keep this in mind as an example, but it doesn't have to be it. It could be anything, any other system. The potential, the external potential that these particles feel could be anything. It could be the box, or the Coulomb potential, or something, whichever. We'll have the basis of one particle state. So if psi blah is a basis, an orthonormal basis of one particle state, the space is called the H1 Hilbert space for one particle. Then this thing, psi k1, answer, psi k2, answer, psi kn, the set of all of these. And since there's too much notation, this will be abbreviated by psi k1, psi k2, psi kn, this thing, the set of all of these. For so K1 to Kn, so as many particles they have, so many quantum numbers they have, from the same range, 0, 1, 2, and these is basis of the n particle Hilbert space, call it H n. So easy. Or why so complicated? Well, it just means sort of independent. What particle 1 does goes into the first slot here, and then what particle 2 does goes here, and you can choose whatever you want, which stay within, and so then this is the basis. And you can of course make linear combinations and make it really complicated. Like you can get entanglement and all this business, right? Before you could, for example, make this fuzzy and this and let this be an eigenstate, or make this fuzzy and this fuzzy, but still keep it sort of disentangled. Some here, and some there, but you can also entangle them. Say if this has a really high energy, then that has to have a lower energy. And then add another term where this is a lower and this is a high energy. So then if you measure one particle, you get high energy, you know the other one has lower energy. Usually, you know this Einstein-Podolsky-Rosen paradox with the two spins and the singlet, and you take them apart, you very far, you make a measurement, spin down. Oh, this has spin up, and it behaves as if it has spin up, like in Stengel, it would go up. It knows action as a distance, things like that. Yeah, so you can entangle them. And you can only entangle them if you can take linear combinations of them. All linear combinations is this. Now that would be so easy if the particle would be distinguishable. Like you have two, and you know the one that's a little bit more pointy is number one, and is number two. But if they are quantum particles, none of them is pointy, or if one is pointing out, they all look the same. They look exactly the same. You cannot even see if you had soccer ball or chocolate pieces that would be absolutely identical. You could still distinguish them by following one with your eye. Number one is the one that I'd never let my eyes off. And you can do this because there's a classical trajectory. I can classify this as a trajectory. I can't. It's so boring, but I could do it. In quantum mechanics, there's no trajectory. There's just the wave function with probability. And if you don't look, it is everywhere. And even in principle, you can't just track them. So identical particles, if it's what's it called, an electron and a proton, of course you can take your eyes, well, you know which one it is. They are distinguishable because they're not identical. But identical particles like electron are truly non-distinguishable, and then you have to have a wave function that doesn't distinguish them. So what is here really needs to be there too. So then starts the business of symmetrization. You have to have a state. So example, if I have a psi 0, psi 2, psi 2 state, so three identical particles say in this state. It's one that I have just claimed there exists. This is not allowed, it's not a physical state of the system, because it would single out number one. It would be something special, but it cannot be. So it has to be symmetric. So what is a good state? You put plus there, then you symmetrize. So you have psi 0, psi 2, psi 2, plus psi 2, psi 0, psi 2, plus psi 2, psi 2, psi 0. So these are the ones I just defined. Now I've symmetrized them. Now I make it too big because I want to observe the norm. They should all be orthonormal. So the square of this is what? 1 plus 1 plus 1, right here also. If I square the thing, I only get the pure squares. The mixed terms are 0, so that's 3. So I think 1 over square root 3. Now that's normalized, and that's a physical state, which means it's a little plus. And the picture, my favorite box is, so this is 0, 1, 2, 3, the levels. Now I have 3 particles. And now I can put 3 things in there. So particle 1 is 0, particle 2, or one of them is here, one of them is there, one of them is there. I don't know who it is. They're all red. We don't see the difference. So this state is this picture. The boxes are the one particle states that are available, these here, and I'm making a 3 particle state out of it. I'm just filling them, and I'm saying which one particle type. And since they are not distinguishable, I have to always symmetrize them. It's really awkward. The plus. Let's get off this anyway. But then the state is unphysical. Only the squares, the absolute value squares are physical. So it doesn't have the wave function doesn't have to be symmetric, just the probabilities that result from squaring the thing. So I could also have anti-symmetric things. So I could also have states that are not plus, but minus. Side 2, side 0, and then I've just taken a simpler example. Why have I taken a simpler example? Because if I took anti-symmetrizing something, A times A minus A times A is not. I can't anti-symmetrize 2 copies of the same thing. So this is the called, this is called some principle, the Pauli principle, exactly. And they are called fermions. And they are called bosons. So particles with a symmetric wave function are called bosons, and particles with an asymmetric wave function are called fermions, and that's just a name for it. You can have both names.
Know that this symmetrization is more of just a snapshot in time. You can always switch any of them, but technically if I have two particles that are far away enough from one another and then I let time go, then they couldn't have evolved into each other yet. And then technically they are kind of distinguishable, no?
Isn't there always just a chance that they can still change places even if they're far away?
Yeah, quantum mechanics is non-local. And you have the wave function, it could be really, really far. That's at least the idea. It's hard to believe for me too.
Only if
Earth and Moon, and if you can, people can, this is amazing. They can actually entangle these particles.
yeah, but
See,
only if they're entangled. I mean, okay.
then you can measure it, but if you don't entangle them, you measure the electron. You don't know if it's the one that was a second ago in the other space.
You don't, I mean,
How do you know? It's just you measure it. It could.
well, if
there's
it travels
just-
over speed of light. Yeah. Doesn't already have a probability in the other place.
I don't know. There's just one thing with the probability of finding a particle there. We never write down a wave function which says the probability of particle one finding there is very low, or one very high there, if the two are identical. If you have an electron and proton, then of course, yeah, then you have the lower and lower probability to find the proton here, yeah, because it has just been seen over there. But if it's two identical particles, it's just the common thing. That's the idea, the structure.
I guess there's no point in saying.
Yeah,
oh,
right,
this
so
is
that-
what-
This isn't super important for the concept, the plus and minus, so let's just stick with the bosons for the discussion now. Let's keep it simple. Here you have all the signs. You wonder, why does this get the minus sign and not that one? It doesn't matter because the overall phase is it's not determined. So let's just stick with the bosons. I can I'm not going to. In my notes, there's a formula general how do you, like there's a symmetrization operator, doesn't really help us. I think I want to get to creating a part. We can- So what we need now is the direct sum of all these Hilbert spaces. Oh. For systems with undetermined particle number, we take the third sum of all n particle Hilbert spaces. So Then this gets the name page F or Fock. And then we have the zero particle Hilbert space. This is just the vacuum state. There's nothing, no particle, just one state in the whole Hilbert space. One of the zero is nothing. Plus our where's the state? I think this should go here. And because there, so this is the one particle. This is what we have. Then we can have two particles, and then we can have. And all the way up to infinity. And if you wanted to denote the plus minus business, we can say if you have bosons, we pick the states that are symmetrized. If you have fermions, we pick the states that are antisymmetrized. So this is the restriction, the plus is the restriction of the space spanned by these with the additional symmetrization and that with the minus with the antisymmetrization. Don't really pay too much attention, it's not important. It's a technicality that doesn't add too much. Here, one particle you can't symmetrize, antisymmetrize, no particle you can't antisymmetrize. Symmetrization of plus minus. And so these guys contain now states, whatever. They contain what? Psi 1 plus psi 2 psi 0 plus da 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 with some coefficients. So yeah, that's now a state with one particle with superposed with a state two particles in very different one particle states, and that's what's going to happen. A system with an undetermined number of particles. Yes?
What I don't really understand, what is this Hilbert space with no particle? Because we are starting from regular quantum mechanics, right? So what?
No,
do I
it's
know?
basically an empty. Oh no, exactly. No particle. No particle.
Yes, but what?
All gone.
What would
And
a
it
Hamilton
all-
operator do? What would a Hamilton operator do, for example, with X?
Nothing. It's really trivial. I mean, you're worried about why do you do different. It's really just for completeness. It's like why do we add the number 0 to the numbers? It's just nothing. Everything with zero. There's no money. There's nothing. It's just boring. Let's not. But you have to have it in case there's sometimes nothing. You start with an empty box. Then this system is in the state. Nothing. It's a name. We'll call it. So this is really just. I'll call it like this. It is different, very different from this. Why?
Yes.
This is the ground state of this one particle not moving much. The ground. And this is there's not even a particle.
Yeah, but I think it's like it's quite a new concept, right? Because in the Schrödinger cases, like we only have a Schrödinger equation if we have a system. So there needs to be something there. We don't even write down a Schrödinger equation when there's nothing. Right?
Exactly, because in chapter 1.2 we had one particle quantum mechanics. There's this one particle. And now we want to create particles. So then we wanted to describe the 4 or 5 particles with a fixed number, how they do their interactions or not. And you know, this symmetrization already is a kind of interaction, and you can show the bosons are more likely together than fermions. So anyway, we have these in particles, and now we want to have at least the possibility to go from a state with one particle after some shaping to 2 particles. And so that I imagine there's an operator that does that acts on one particle state, so from something from here and moves us there. Or we've seen it basically from there to there, you create a particle antiparticle pair, usually come in pairs, because you want to conserve charge. Maybe this is your concern. How do you get nothing? I mean, where is it gone? Like, how can this disappear? It doesn't seem to conserve anything.
Yeah, and don't we have we already introduced the concept now that there is such a thing as completely nothing.
Yes.
Like there's no quantum system whatsoever.
No,
Or no.
there's just, this is called the vacuum.
Yeah, but it's,
you know,
yeah. It's
this will be
debatable
the-
if it really exists, like nothing. That's
Yeah.
like,
you know, well, we have. I don't know how to say, we will build everything basically from nothing, so we have nothing and then we use creation operators that we don't have yet.
Yeah.
So in the same way, we created excitations of one particle with creation operators. They were called, we have something here too, and then we have a raising. If you, nobody is ever precise again, but for this moment, so you raise the energy, you raise to a higher excitation, so you have a raising operator of dagger that we had. Then you have something that goes down, this is the lowering. In a minute or not, maybe in 22, maybe in 22 hours, I will introduce a dagger, and that is a creation operator. The name is creation operator, and what it does, it will create one of these particles, and it gets a little label so that it knows in what state it should, and it can add more things. And then I have a conjugate, this is the annihilation operator that takes it away. And then I have, so this moves here. From here, it's the A dagger, and this way, it's the A without the dagger. So you go from this chain, and then you say, oh, there's the lowest one, and that is annihilated, and that's the vacuum. And then we build the one particle state from the vacuum with one creation operator, not with a raising, because there's nothing to raise in this space, but we create and go there. And that's how when you think of an empty universe, nothing in this state, okay, nothing will ever happen. But then what we'll do, we want this, do you remember in the beginning, we wanted to scatter electron, and see what they do? We create an electron in the one particle state K. This K then says, oh, my electron is very fast. Okay. If it's a large K, it's up here, it's a very fast electron, and then you create your electron and we shoot them, and your electron will be a little less K, say, but your spin is maybe up, then you have another quantum number, all this stuff. And then we have the two things, and then they can. So this is a really boring state, like the 0 euro state of the wallet, but it needs to be there just for completeness, and you fill your wallet with the creation of it.
Yeah, so it's more, it's more a mathematical thing, because if it's really physical, if the state really exists, is questionable, right? If we would ever really
won't
get
be
into.
here, yeah, exactly, nothing would be there, it's the vacuum.
Yes.
Zero.
So it's like a mathematical tool in order to have, we need to have this for all these. Okay.
Yeah.
Okay.
Yeah. Now I fulfilled my promise to create a particle. Did I? I guess somehow. We'll move on from there to tomorrow. Are there any like open questions, something urgent that will you keep awake now? Well, then let's go to sleep, I guess.
You can start.